Welcome to CP 329. We're going to cover digital analog converters. In this lecture, we're just going to concentrate on the construction and operation of digital analog converters. A digital analog converter is a device that converts an N-bit digital value to a corresponding analog voltage. And you'll be using this as part of your function generator project 2. So how do we create an analog voltage? Well, we can start off by using an op-amp here, and if you remember your op-amps, basically no current's going into this input here of this op-amp, and because of that, this amplifier here is going to have this voltage, kind of a voltage sharing thing. Remember, the current here is backwards, so there's a negative there. So we're going to have a VRF divided by R, and it's going to be minus that. And so here, this could be the voltage reference, and this is our output here. And if we can add more voltage references with more resistors here, so now this is going to be a summing amplifier here, because now it's these two resistors in parallel here, and there's on the bottom. So it's going to flip up to the top here. So now it's twice that. And we can continue this process here, but let's be a little bit intelligent here. So here we're showing 4 resistors, but we're gonna grow them, right? So and so here R3 is going to be R, then 2R, then 4R, and then 8R. Now we have a combination here based on these switches of having, I guess, 0, and then R, 2R, 3R, 4R, 5R, 6R, 7R, 8R, all the way up to 15R, I guess, total. And where these switches here, what we can think of is they'll be controlled digitally. So our N-bit digital vector will determine whether or not these switches are closed or open. And so if this is 1, 1, 1, 1, then all of these switches are on. All of these resistances will add up. And so that's exactly what a digital to analog converter is. Pretty simple circuit. And so we'll do a couple examples here. So if we have binary input B3, B2, B1, B0 equals 0, 0, 0, 1, so 0, 0, 0, 1, this guy will be on, the rest of these are off, and so we get this connection here, and so we're going to have I1 here is going to be equal to these things, right? So VREF over R0 equals VREF over 8R. And likewise, if it's 9, then we have 2 paths are on, and these things will sum up. And so we have 1 plus 1/8. So in general, it will look like this. The amount of current looks like this. And so here we're doing all the summing here of all the resistances, and the B's are there just to notate whether or not they exist or not. So in general, the output here is going to be there's going to be a reference voltage, and it's going to get divided by 2 to the n minus 1, where n is the number of bits in the system. And then we're going to have a resistance ratio here, and it's going to be the sum of the bits weighted by the power. Okay, so I guess the result of this is that in general we're going to be able to create 2 to the n minus 1 voltage steps. And so those 2 to the n minus 1 voltage steps look like this. And if we could look like this, if we have a lot of bits, it will look nice and smooth. But if you zoom in, it's going to be discrete steps of voltages. And so that is so this type of error here, this DAC resolution, will be better with more bits. And so depending on the type of digital analog converter, you may have more or less bits. So as you can imagine, more bits in your digital analog converter will be more expensive. The other resolution is the width of these time steps here. So each of these time steps could be wider or smaller depending on the rate at which your DAC can work. and so that's kind of proportional, sometimes proportional to the sample frequency. I guess it's that's more of a function of the analog to digital conversion and how often you read that circuit. Okay, so again, this, if we have less bits, then it looks less smoothly. It looks more pyramid-y or staircasey like that. Okay, so let's take a look at a particular DAC. This one is one that's on the PMODs from Digilent on their Nexus boards, and they use a 12-bit DAC, but it's not required for this course. You could use less bits and do just quite fine. And so it has a wide voltage range. It can go from 2.7 volts to 5.5 volts. That's a pretty nice range. It has a power down feature. That's not too important. It uses a 3-wire serial interface called SPI, and we've already covered that in this class. And so here the SPI line, you kind of have to read into it a little bit. S clock is serial clock still, but this here is the say select here, and it's active low. And since this is an output device, it only has a data input, so the master out slave in, the MOSI line, would have to be connected to this. And then, so this data sheet says that this particular DAC runs on a 30 megahertz serial clock. And so in general, since it's 12 bits, you're going to have all the way down to 0 up to 4095 are all the steps, right? So there's 4,000 or 4K steps up here, and each one is, so this voltage here is going to be whatever the reference voltage is, VA, times 1 over 4095. And so let's say the reference voltage is 5 volts. This is going to be 5 volts divided by 4095. It's going to be very, very small. Up here, so if we go up halfway to 2048 over 4096, and VA was 5 volts, it would be 2.5 volts. And this would be approximately 5 volts. It's not going to quite get there, but it's probably close enough for most operations.